Today's lesson is about the ideal gas law. We have been using only 3 variables for the past few lessons, but today we're going to introduce the 4th variable. Remember, we have been talking about pressure, volume, and temperature. For ideal gas law problems, however, it's going to be important that pressure is always calculated in ATMs, volume is always in liters, and temperature in kelvins. The 4th variable is the mole, and we're going to use the letter N to represent the mole. Now, because our problems are not always going to be given to us in atmospheres, liters, kelvins, and moles, let's do a quick review of some important conversions. When talking about pressure, sometimes the problem will be given to us in millimeters of mercury, or torrs, so we will have to convert them into ATMs. Our volume, which should be given to us in liters, may come to us as milliliters, cubic centimeters. We need to remember that 1 liter is equal to 1,000 milliliters, 1 liter is equal to 1,000 cubic centimeters, and a milliliter and a cubic centimeter are the same, except milliliters measures the volume of liquids and gases, and cubic centimeters of solids. Our temperature scale, we have to add 273 degrees to the temperature given in degrees Celsius. Again, let me say that again. In order to go to degrees Celsius, you have to add 273. Now, when it comes to the mole, sometimes they're going to give us the problem in grams, and we will have to convert our grams to moles. Remember, we're going to use the periodic table where the mole is set equal to 1, and you have to look up its molar mass and then convert it. So let's begin. In order to write the ideal gas law formula, we have to introduce Avogadro's concept about volume and moles. He basically says that volume and moles are directly proportional when dealing with a gas. What this means is if you increase the number of moles, or the amount of substance that you have, the volume or the space it takes up also increases. This is a directly proportional relationship, and we write that formula as V is equal to K times N, where K is a constant. We're going to solve this equation for K and get the equation V divided by N equals K. Now, as you recall, we talked about Boyle's, Charles, Gay-Lussac, and Avogadro, and we said that Boyle's law was indirectly related, so P times V equals K. Charles was volume and temperature were directly proportional. Gay-Lussac, pressure and temperature directly proportional, and Avogadro directly proportional. What we do notice is that all of these equations are set equal to K, so we can combine them into a new statement. Remember, pressure is on top, pressure's on top, pressure goes in the numerator. Volumes in the numerator, volumes in the numerator, volumes in the numerator, volumes in the numerator. Temperature now is in the denominator, and the mole is in the denominator, and we let them all set equal to K. Now we're going to replace K with the letter R, because K is just a unique variable to algebra. We want our chemists and our physicists to recognize that we're dealing with a gas law. And when that happens, we are going to use the letter R. R is a constant value. What is the constant value? The constant value is always this. But let me explain how we get to that. What we do is we take this equation here and we set it to STP, and we replace pressure with 1 ATM, because standard pressure is 1 ATM, and we have to multiply by the standard volume, which is 22.4 liters. We divide by the standard temperature, which we learned to be 273 K, or 0 degrees Celsius, and then we need the standard mole, and we always set the mole equal to 1. So basically what we're going to do is take 22.4 and divide it by 273 and get 0.0821. The units are the hard part here. None of my units cancel out. So I have to bring them all over here, and I write atmosphere liter. Now that doesn't mean it's a negative sign here. This dash means that atmosphere and liter belong together in the numerator. And then my mole and my Kelvin are going to go together in the denominator, and I write it as mole Kelvin. This is my R value. Now what we have then is a new formula. We have PV divided by Tn is equal to K, which we replaced with the symbol R. What we want to do is get rid of this denominator. So we're going to multiply both sides by Tn, and we're going to get PV equals R Tn. Now we don't write it in that final format. We rewrite it so that on this side, the RTN is written as nRT. And this is the ideal gas law. PV equals nRT, or it's known as the perv-nert relationship. PV equals nRT. Let's put it to work. Here's my first example. How many moles of gas does it take to occupy 120 liters at a pressure of 2.3 atms and 340 K? So how many moles? That means that I am looking for N. I have 120 liters, which is my volume. I'm at a pressure, 2.3 atms, and my temperature is 340 K. It's really important that my pressure units are in ATM, my volumes in liters, and my temperatures in Kelvin. Since they all match up, I don't have to do any conversions in this example. I am solving for N, so I'm going to record my ideal gas law problem here. PV equals nRT. I circled the N because that's what I'm looking for, so I divide by RT on both sides. I substitute in for each of those letters, and now it's important that we understand how the units cancel out. This ATM is in the numerator, this ATM is in the denominator, they cancel. Liters is in the numerator, liters is in the denominator, they cancel. This Kelvin is in the denominator, and this Kelvin is in the numerator. It goes top, bottom, top. So my bottom here will cancel my top and leave me with MOL. That MOL, because here's the denominator, this is the numerator, our answer will be in moles. So 2.3 times 120, divide by 0.0821, divide by 340 to get my answer.